Welcome back, dear students. This is part 3 of types of evidence. We are going to continue second type of evidence, part 4, perpendicular bisector theorem. Remember, the perpendicular bisector of a segment is a line perpendicular to the segment at its midpoint. In this figure, we have this blue line is the perpendicular bisector of segment AB. It divides AB into two equal segments. C is a point on this perpendicular bisector. The theorem says any point on the perpendicular bisector of a segment is equidistant from the extremities of the segment. Here we have C is at equal distance from the extremities of segment AB. If I move point C, it will always be equidistant. Here, if it's the midpoint of AB, it's also equidistant from the extremities. So wherever I move point C, it's always equidistant at equal distance from the extremities of segment AB. So here, if you see these images, wherever I place point C on the perpendicular bisector, it's always equidistant from the extremities. Example, in this adjacent figure, BD is the perpendicular bisector of segment AC. When I say BD, the line passing through points B and D, is the perpendicular bisector of AC. Write the evidence that we can claim and state the reason. Here we don't have any straightforward evidence. All the evidence that we can claim are related to the definition and the theorem related to the perpendicular bisector of a segment. By definition, we can claim that angle BDA equals angle BDC equals 90 degrees, perpendicular bisector effect. We can also claim that DA equals DC because D is the midpoint of segment AC. DA equals DC, perpendicular bisector effect. Also, we can say midpoint effect. And using the theorem, we can claim that BA equals BC since B is a point on the perpendicular bisector of AC. BA equals BC. But here the reason is because B is on the perpendicular bisector of segment AC. Or we can say because B belongs to the perpendicular bisector of segment AC. Remark, the perpendicular bisector of a segment theorem is used to prove that two segments are equal. So here, in case you want to prove that two segments are equal, and in the given, we have information about a perpendicular bisector to a given segment, we can use the theorem. Now, part 5, converse of the perpendicular bisector theorem. The converse says every point which is equidistant from the extremities of a segment belongs to the perpendicular bisector of the segment. Here we have a segment and we know that MA equals MB, NA equals NB. These are the given information. If I draw a line passing through these 2 points M and N that are equidistant from the extremities of the segment AB, we will notice that the line MN is in fact the perpendicular bisector of segment AB. We use the converse of the perpendicular bisector theorem to prove that a point belongs to the perpendicular bisector of a segment. Let's see this example to understand this converse more. Example, in this adjacent figure, BA equals BC. So in this figure, we have BA equals BC. Prove that B belongs to the perpendicular bisector of segment AC. Here to prove that point B is or belong to the perpendicular bisector of segment AC, I need to have the fact that a B should be equidistant from the extremities of segment AC. Here we can claim the fact that B is equidistant from the extremities of segment AC because BA equals BC, it's given to us. Proof: since BA equals BC given, we can claim the fact then B is equidistant from the extremities of segment AC, and by using the converse of the theorem, we can say that point B in fact belongs to the perpendicular bisector of segment AC. Result: B belongs to the perpendicular bisector of segment AC. Now exercise in this adjacent figure, AMN is an isosceles triangle of vertex A. NMB is an isosceles triangle of vertex B. Prove that the line AB is the perpendicular bisector of segment MN. In this exercise, we need to prove that points A and B are both equidistant from the extremities of segment AB in order to prove that the line AB is in fact the perpendicular bisector of MN. Let's start with point A. Can we claim that A is equidistant from the extremities of segment MN? By looking at the given information here, it's not straightforward. By using the property of the isosceles triangle, we can claim that AN equals AM. They represent the legs of this isosceles triangle. Same for point B. We can claim that BM equals BN, legs of the isosceles triangle NMB of vertex B. So AM equals AN and BM equals BN. So proof: AM equals AN. The reason here that it's not a straightforward evidence, it's not given, we deduced it. Represent legs of isosceles triangle AMN of vertex A. BM equals BN, legs of isosceles triangle BMN of vertex B. Then A and B are equidistant from the extremities of segment MN. So now these 2 points are equidistant from the extremities of segment MN. The result here is that the fact that the line AB is the perpendicular bisector of segment MN. Result: AB is the perpendicular bisector of segment MN, because once we prove that A and B are equidistant from the extremities of segment MN, it means that these 2 points, they both are located on the perpendicular bisector of the segment MN. So the line passing through these 2 points is in fact the perpendicular bisector of segment MN. Now part 6, rectangle properties. ABCD is a rectangle. Remember, a rectangle is a quadrilateral having 4 right angles, as you see. Property: the opposite sides of a rectangle are equal. Here AB and DC are opposite sides. They are equal. Same for AD and BC. Both pairs of opposite sides are equal. Example: in this adjacent figure, ABCD is a rectangle. As you see, E is a point on the semiline CX and F is a point on the semiline AY. Write all the possible evidence that we can claim and state the reason. So using the definition of a rectangle, we can claim that the 4 angles are in fact right angles. Also, we can claim that the opposite sides AB and DC are equal. AD and BC are also equal. Remark: if we extend a side of a rectangle, we can easily deduce the fact that the exterior angle is a right angle. Here, for example, if we extend the side CB, CX is the extension of CB, we can claim that ABX is in fact a right angle because here the points CB and E are collinear. Same for the side AD. If we extend it, the exterior angle here, we can claim that it's a right angle. So both angles here, both exterior angles are right angles. Since points CB and E are collinear, we can easily deduce that ABE is a right angle. And since point ADF are collinear, we can easily deduce that CDF is a right angle. Attention, DCB, DCE, and DCX are three names of the same angle. So they represent the same angle. When you want to name this angle, you choose one of the three names, so be careful. Solution. So angle DAB equals ADC equals BCD equals CDA equals 90 degrees. The reason here, angles of a rectangle. Also AB equals DC. The opposite sides of a rectangle ABCD are equal. Here we cannot write given. We claimed these evidence because it's given to us that ABCD is a rectangle. So when I write the reason, I write the properties of the rectangle that I used. Also, AD equals BC, they also represent the opposite sides of a rectangle ABCD are also equal. We can also claim that angle ABC equals ABE equals 90 degrees because points CB and E are collinear. It means they are located on the same line. Also, angle CDA equals angle CDF equals 90 degrees, also because of the points AD and F are collinear points. This is the end of part 3. Thank you for watching and see you in part 4.